Good morning everyone. This is Sathish Kumar from Electrical and Electronics Engineering Department. Today I am going to teach back EMF in DC motor and types of DC motors and also torque equation of DC motor. So before going to discuss about the back EMF in DC motor, the principle of the DC motor is nothing but Faraday's law of electromagnetic induction. But the construction of the DC motor is similar to the DC machine only. Not similar, the almost same. But according to Faraday's law of electromagnetic induction, a current carrying conductor, if you are placed in the magnetic field, then EMF will be induced in the coil. That induced EMF is always opposes the rate of change of flux linkages. According to Lenz's law, that is E is equal to minus n into d pi by dt. So, in case of the DC motor, we are getting the back EMF. So, when the armature conductor of the DC motor will be rotates according to the principle of the DC motor, the armature winding will be rotate, field winding will be constants. Means, in this case, the armature of a DC motor will be rotates, then the winding or conductor on the armature also rotates in the magnetic field. In case of the DC machine, we are getting the induced EMF. That induced EMF is dynamically induced EMF. So we discussed it earlier on. Because what is meant by dynamically induced EMF? In case of the DC machine, conductor or coil will be rotate, magnetic field will be constant. So that's why we are getting the dynamically induced EMF. So according to that one, here armature of a DC motor will be rotates, means that is nothing but as the winding or conductors on the armature also rotates in the magnetic field. So according to Faraday's law of electromagnetic induction, we are getting the EMF in the conductor. That EMF direction will be found by Fleming's right hand rule. That is in opposition to the applied voltage. According to the Lenz's law, that is E is equal to minus n into d pi by dt we are getting. So the EMF induced in the armature winding is in the opposite direction, hence it is referred to as a back EMF of a DC motor. Because whatever the induced EMF you are getting in the armature winding, that is the opposite direction. That's why it is referred to as a back EMF of a DC motor. That is denoted with back EMF is denoted with E suffix B. This is the symbol of the back EMF in case of the DC motor. Means this back EMF will tries to opposes the supply voltage or applied voltage. Supply voltage or applied voltage. But it is has to drive the armature current, that is I suffix A, against the opposing of this back EMF EB. Against the back EMF of EB. So you can observe here armature current IA. This is the I am taking the one DC motor. So this is the armature winding. This is the supply voltage I am taking or applied voltage I am taking. So this is the back EMF will be produced here. Means induced EMF will be produced in this armature conductors. So this induced EMF will be always opposes this supply voltage. So that will be referred to as this is the back EMF I am saying. So I am getting the current here. That current will be always opposes here. According to here, that current will be opposing of this back EMF EB. So this armature current IA is equal to net voltage by resistance I am taking. That net voltage is equal to nothing but what? I am taking the here induced EMF EB and the voltage across this armature winding V. So net voltage is equal to what I'm getting? V minus E suffix B, EB I'm getting. So IA is equal to net voltage by resistance. Which resistance you need to take here? Armature resistance we need to take. So that's why I suffix A is equal to net voltage by resistance. That net voltage is equal to V minus EB divided by armature resistance R, where R suffix A is equal to, I am telling as the armature resistance, and this expression induced EMF or back EMF is given by, according to the EMF equation of the DC generator, E is equal to P pi NZ divided by 60 into A. Here I am taking here E suffix EB is equal to what I am taking, same P pi N. This is the into P pi NZ divided by pi into Z into N into P divided by 60 into E, where pi is the flux per pole, Z is the number of conductors in the armature, and the N is the speed of the armature winding, and the P is the number of poles in the winding, and A is the number of parallel paths. So this number of parallel paths according to the winding only, that armature winding will be divided into two types again. What are that is? Lap winding and wave winding. In case of the lap winding, number of parallel paths is equal to A is equal to P. In case of the wave winding, number of parallel paths A is equal to 2. So that will be same. Whatever the DC generator we are discussing, same thing only we are getting. So means this back EMF will be, depends on the armature speed here. Depends upon the armature speed. If this flux will be constant, the number of conductors will be constant, poles will be constant, and the parallel paths will be constant. But which is the variable here? Only the speed will be variable. That's why this back EMF will be depends upon the armature speed. If speed is high, then what will happen? Back EMF is also high. Hence, if the back EMF will be high, then what happen? Armature current will be small, because here back EMF will be opposes the armature current now. So that's why if the speed will be high, EB is also high. Hence, armature current will be reduces. That is called as a small. If speed will be less, then induced back EMF also less. If the back EMF will be less here, then what will happen? Armature current will be high. So means more current flows here. So if the current flows will be more, that develops the back EMF will be develops the torque in the conductor. Okay. So then we'll discuss about torque first. So we'll get the torque now. So torque. So before going to torque here, we know that induced EMF in a DC generator is same, that is P pi NJ divided by 60 into A. This is into. So in case of the DC motor also, EMF is induced in the same way, but it is in opposite to the supply voltage. It is opposite to the what? Supply voltage. That's why this is called as a, what I am saying, back or counter EMF I am telling you. So that's why the formula is same, that is EB is equal to P pi Zn divided by 60 into A. So then what I can write now, in case of the classification of the generator motors you will get. So in case of the classification of the motor, EB in case of the DC shunt motor, E suffix B is equal to V minus IA into RA for DC shunt motor, where EB is equal to P pi N divided by 60 into A. In case of the series motor, EB is equal to V minus IA into RA plus RSC, for this is DC series motor. We'll discuss this, what is my shunt motor, what is my DC series motors. Okay. Now, we'll discuss. According to, this is the back EMF you are getting. So this back EMF will be varying, or supply voltage will be varying, or terminal voltage will be varying according to the classification of the motors. So this classification is similar to the DC generator classifications only. What is the DC generators classification? We have the two types. What that is? Self-excited DC generator and as well as the separately excited DC generator. Similarly, in case of the DC motor also, we are getting here two types. So now we'll discuss about the self-excited DC generator. In case of the self-excited DC generator, we have the three types of the DC motors are there. That is what? DC shunt motor, DC series motor and DC compound motor. Now we'll discuss about the first DC shunt motor. Sorry, we'll discuss about first DC series motor. You can observe here. What is meant by DC series motor? Series is nothing but in case of the self-excited DC motor, armature winding is connected in series with the field winding. Armature winding is connected in series with the field winding. That is called as a DC series motor. That is called as a what? DC series motor. Okay. So, in case of the direction of the induced EMF in case of the DC generator, that will be depends on the Fleming's right hand rule. But in this case, Fleming's left hand rule according to the Lenz law. So now, what I am getting now, this is the, in case of the DC motor, what is the function of the DC motor? It converts electrical energy to the mechanical energy. Means we are giving the electrical energy to the supply to the motor. So that's why I am giving the DC supply I am giving here this terminal. So means line current will be flowing through this series field winding and series field winding current will be flowing to like this. Means I am getting here this back EMF is whatever the induced EMF will be produced in this armature conductor, that induced EMF will be opposes this armature current. But in case of the DC series generator, that is not possible because both are is in the same direction. Armature current and the induced EMF will be same direction. But in this case, induced EMF is the one direction and the armature current is in the another direction. Means it will be opposites or not here? It will be opposites here. That's why I am getting here. Which EMF I am getting here? Back EMF or counter EMF I am getting. Okay. So, in case of the series motor, the field winding of these motors is connected in series with the armature and carries the same current here. So, because these all are connected in the series, that's why what I am getting now, IL is equal to, what I am getting now, IL is equal to, ISC is equal to IA I am getting. So, because all are connected in the series. Okay. So, now, what I am saying here, IL is equal to ISC is equal to IA. Now, you can apply here loop analysis. If you are applying the loop analysis, what I am getting now, V is equal to EB plus IA into RA plus ISC into RSC plus BCD is nothing but is what? Brush contact drop. Okay. Now I am taking here V is equal to EB plus IA into, because ISC is equal to IA. So can I write now ISC is equal to IA is nothing but I am substituting here. In case of the ISC, IA I am substituting. Now here taking the IA is common here. And what I am getting now, V is equal to EB plus IA into RSC plus RA plus BCD I am getting here. So where BCD is the brush contact drop, this brush contact drop is usually 1 volt per brush, where RA is the armature winding resistance, RSC is the series field winding resistance. This is the voltage equations of the DC series motor. Now, next is DC shunt motor. In case of the DC shunt motor, what is the DC shunt motor? Armature winding and the field winding both are connected in the parallel. So that type of motors I am calling as a DC shunt motor I am calling. So means in case of the DC shunt motor, the field winding and the armature winding both are connected in parallel. So similarly I am applying the supply voltage, that is the VDC supply I am getting. So then this is the line current will be going here. This line current will be divided here too, that is armature current here and the field winding current here. Again, this also induced EMF will be opposes this armature current only according to the back EMF. So now in this case, whatever the voltage across this one, this voltage will be same because this all are connected in the parallel. All are connected in the parallel. Can I write now? This IF is also I am writing as a ISH because shunt field winding. You can call, some people are calling IF, some people will call the ISH. Okay. Now IL is equal, you can apply here what here? KCL. Current entering into the node will be is equal to current leaving the node. So then IL is equal to what I am getting now? IA plus ISH. IA plus ISH. Then where ISH is equal to what? V by this. Because what is the voltage I am getting here? V. Supply voltage is V. So I mean the supply voltage V. Whatever the voltage V here, same voltage will be there is a across the shunt field winding because both are connected in the parallel. So that's why what I am getting now here, ISH is equal to V by RSH. Okay. Now you can apply here what again? Loop analysis. If you are applying the loop analysis, V is equal to EB plus IA into RA plus BCD. Where BCD is nothing but is what? Brush contact drop. 1 volt per 1 brush. So this is the voltage S and current equations for DC shunt motor. Next is compound motor. That is here short shunt compound motor. So you can observe here, this it is the short shunt compound motor. In case of the short shunt compound motor, armature winding is connected in parallel with the shunt field winding. Again that will be connected in series with the series field winding. Means it is a combination of shunt and series field windings. But shunt winding is connected across the armature only. Again that is the parallel with the armature only. Hence this is in case of this that's why this is called as the short shunt motor I am calling. So in case of the short shunt motor also, I am giving the supply voltage, what here? V. I am giving the supply voltage is V. So then line current will be going through field winding, that is I am getting a series field winding current, and here armature current IA. This armature current IA is opposes the induced EMF in the armature winding. Okay. So then this is the current dividing here. This I suffix A current will be going downside here. ISH will be going here like this. So now what you can write now? IL is equal to, can I write now? IL is equal to IA into ISH. IA into I suffix SH. IL is equal to IA plus ISH. Because I am applying here what here again? KCL. Current entering into the node will be is equal to current leaving the node. So where can I write IL is equal to ISC? Can write now. IL is equal to ISC. I am writing here. Because both are connected in the series here. So now what you can write now? ISH is equal to, this ISH is equal to, what is the voltage here? Because this is not the parent. V plus ISC into RSC. V plus ISC into RSC divided by RSH. Divided by RSH. So because this is the ISH. Okay. So because why I am getting the V plus ISC into RSC? Because the voltage across this shunt field winding is same as the voltage across voltage of this all things. So then voltage of this all things in the terms of what? V minus V plus ISC into RSC. This is the series field winding resistance. RSC divided by what is the shunt field winding resistance? RSS. Then what I am getting now? I suffix SH I am getting. Shunt field winding current I am getting. Now can apply here loop analysis here. Then what I am getting? The terminal voltage or supply voltage in terms of the back EMF. This back EMF is opposes the supply voltage or not? Supply voltage or terminal voltage. So then what I am getting now? V is equal to EB plus IA into RA plus ISC into RSC plus BCD. Where BCD in the term is what? Brush contact drop. that is 1 volt per brush. So this is the short shunt compound motor. Okay. Next is long shunt compound motor, because the compound motor is classified into two types. One is the what? Short shunt compound motor, another is the long shunt compound motor, according to the classification of the motors. Okay. So now this all are this series motor, shunt motor and compound motor. This all are the what? Self-excited DC motor only. Okay. So now long shunt compound motor. In case of the long shunt compound motor, the short, again I am getting here series field winding and the shunt field winding. Okay, the series field winding is connected in series with the armature winding. This both are connected in parallel with the shunt field winding. Both are connected in the parallel with the shunt field winding, because the shunt winding is connected across the combination of this armature winding and series field winding. Hence, this is known as a long shunt compound motor, I am saying. That is long shunt compound motor, I am saying here. Okay. So, can apply again what here? According to the DC motor function, I am giving the electrical energy is the supply. So, I am giving the supply voltage V, then IL will be divided into two, that is shunt field winding current and a series field winding current. And series field winding current going to here armature current. Here in this case, ISC is equal to IA, because these both are connected in the what? Series. That's why ISC is equal to what? IA. I am getting here. So now, what you can write now? IL is equal to ISH plus ISC. Can I write now? IL is equal to ISC plus ISH. Where can I write ISC is equal to IA? ISC is equal to IA I am writing. So can I write now IL is equal to IA plus ISH? I am writing IA plus ISH. So then ISH is equal to here. ISH is equal to whatever the voltage across this one, both are connected in the parallel. Then what is the voltage here across this shunt field winding? V only. Then V by RSH. V by RSH. ISH is equal to V by RSH. Then again apply your what? Loop equation here. You can apply the loop equation. Then you can write the relationship between the back EMF and the supply voltage here. That is V is equal to EB plus ISC into RSC plus IA into RA plus brush contact. So now, but ISC is equal to IA. Can I write now here E suffix EB plus IA into RA plus RSC plus brush contact drop also. You can write. Yes, sir. Yes. So, this is the what? Long shunt compound motor. Long shunt compound motor. So, this all are the classification in under the what? Self-excited DC generator. Now, we'll discuss separately excited DC generator. This is the separately excited DC generator. Separately excited DC generator is nothing but as a what? We are giving the excitation is separate DC supply to this field winding. Okay. So you can observe here. This is the armature winding. This is the field winding. Both are connected in the separately. In case of the self-excited DC generator, armature winding and the field winding both are connected in the one manner only. Okay. Now, I am here exciting the field winding separately with the DC supply here. Okay. Now, this is the V supply here again, and the armature current IA, and this is the back EMF. EB is opposes this armature current. So, means the field winding of this motor is energized from an external DC source. That's why this is called as a what? Separately excited DC source. Separately excited DC motor I am calling. Okay. So now you can apply here what? Loop analysis. Then what I am getting now? V is equal to EB plus IARA plus BCD. Where BCD is nothing but what? Brush contact drop 1 volt per brush. Okay. So this is about separately excited DC motor. Means we discussed here back EMF of the DC motor, then importance of the back EMF, then classification of the DC motor. Hours. Okay. Now we'll discuss about torque equation of the DC motor. Because due to that back EMF, torque will be produced now. So then what is in torque? Which torques we will be getting in case of the DC motor, that we'll discuss. Torque. Here, torque or moment of force is the tendency of a force to rotate or move an object about an axis is called as a torque. So in case of the DC motor, armature winding will be rotates. Okay. So for example, here I am taking here. This is the armature winding. Conductors. These are conductors. Are placed here. Then some piston force will be applying on this. Okay. So then what will happen? This winding or these conductors will be, if you are applying the piston force here, this conductor will be moves from one position to the another position. Means some distance will be moves here. Okay. So that force into this distance I am calling as a what? Torque I am saying. This is the what? Force into this distance. Means this conductor, means rotating conductor, is rotates with a distance d, okay, or with a radius r. Okay. So this is called as a what? Torque I am calling. Okay. So means a torque is also called as a what? Moment of force is the tendency of a force to rotate or move an object about an axis. This is the an axis I am taking. This is the an axis I am taking. Okay. This a force is a push or pull. Likewise, torque is a fist to an object. Fist to an object. So mathematically, we can define the torque is equal to force into radius. Force into radius. Okay. So now grass torque or what? Armature torque. The armature torque or grass torque I am taking. Then torque units are what? Newton meters. Torque units are what? Newton meters. Okay. Now grass torque is also what? Or armature torque is equal to what? Force into radius. Or radius r is equal to radius of the armature in meters. That is, here r is the radius of the armature in meters. And n I am taking speed of the armature in RPM, that is revolution per minute. That will be is equal to n by 60 RPS, revolution per second. Where F is equal to circumferential force on the armature, where omega is equal to angular speed of the armature. We need to remember this all things. Okay. Now, torque. Work done per revolution are also is equal to force into distance moved per revolution. Okay. So force is nothing but what? F. Into distance moved per revolution is nothing but what? Omega. Or that is nothing but what? 2 pi r. That is nothing but what? 2 pi r. Okay. And work done. This is the work done. What is this? Is which work done I am getting here? Force into distance per distance. I am taking the work done. That is force into 2 pi r. I am taking. That is angular speed. Okay. If you are taking work done per revolution. Revolution is nothing but what? Some seconds. That will be that conductor will be is a rotating part. Okay. So means that will be rotates within a depends on the time. Okay. So that is I am taking here seconds I am taking. If you are taking the seconds, that is force into 2 pi r into n by 60. N by 60. So work done per revolutions in nothing but what? Torque. That is work done per seconds is equal to force into 2 pi r into n by 60 I am taking. Nothing but what? Newton meters. Okay. Or work done is equal to 2 pi n by 60 into force into radius. That is Newton meter per seconds or watts I am taking. That is nothing but what? Power. Nothing but what? Power. Where F into R is nothing but what? Torque. Which torque here? Grass torque or armature torque. That is work done is equal to 2 pi n into T suffix G divided by 60. That is the power. So this is I am taking the equation number 1. You need to remember this. Work done is equal to what? 2 pi n into Tg divided by 60. This is the equation number 1 I am saying. Okay. Then the expression for voltage in DC motor is given by V is equal to EB or EA, whatever it be. Some textbooks will be EB, some textbooks will be EA. Back EMF. Okay. EB plus IA into RA. So you can multiply throughout by armature current IA. Then what I am getting now? V into IA is equal to EB into IA plus IA square into RA. So I am expressing this equation in terms of the words. What is my V into IA in terms of what? Electrical input we are giving to the DC motor. Okay. Is equal to electrical, this EB into IA in terms of what? Mechanical power developed in the armature conductors. Okay. That is electrical power equivalent to the mechanical power developed. Plus IA square RA. That is in terms of what? Armature copper loss I am taking. That is armature copper loss I am taking. So then mechanical power developed is equal to I am taking EB into IA. That is the equation number 2 I am taking. From this equation, mechanical power developed in the armature winding is equal to EB into IA. That is the equation number 2 I am taking. Okay. Now you can compare, or since equation number 1 is equal to equation number 2, means you can compare the equation number 1 and equation number 2. What is equation number 1? Work done. What is the work done I am taking here? 2 pi n Tg divided by 60 I am getting. Okay. Is equal to, what is the second equation? Mechanical power developed in the armature winding. That is EB into IA. Okay. So then from this equation, EB is equal to, what is the EB back EMF? EB is equal to, we derived in the first one. That is EB is equal to what? Pi Zn divided by 60 into P by A. So this is the EB. Okay. That is EB I am substituting here. That is pi Zn divided by 60 into P by A into armature current I suffix A. Okay. So then this 60 will be cancelled. This N will be cancelled. Next what will be cancelled? No another things will be cancelled. Now from this equation, I am getting the gross torque or armature torque Tg is equal to 1 by 2 pi into pi into Z into Ia into P by A. Okay. So if you are simplifying this, 1 by 2 pi is equal to 0.159. That is 0.159 into pi into Z into Ia into P by A Newton meters. This is a what? Gross torque or armature torque, where pi is the flux per pole, Z is the armature conductor, I suffix A is the armature current, P is the number of poles, A is the number of parallel paths. Okay. Hence, torque of a DC motor is directly proportional to the flux per pole and as well as the what? Armature current. But torque will be always directly proportional to the flux per pole as well as the what? Armature current. Okay. So this is the what? Gross torque or armature torque equation of DC motor. That is Tg is equal to 0.159 into pi into Z into Ia into P by A, where pi is the flux per pole, Z is the armature conductors, I suffix A is the armature current, P is the number of poles, A is the number of parallel paths. This number of parallel paths will be depends on the armature winding. If it is a lap winding, A is equal to P. If it is a wave winding, A is equal to 2. Okay. Then this armature torque or gross torque is directly proportional to the armature current and as well as the flux per pole. This is the armature torque or gross torque. Then she will take relationship between the armature torque and shaft torque and loss torque. Okay. So then we know that gross torque is equal to 1 by 2 pi pi z into Ia into P by E. Okay. So now we can rewrite this equation also like this. EB into Ia divided by 2 pi n by 60 also you can write Newton meters. Okay. Now the total motor output is equal to what? 2 pi n divided by 60 into T suffix s, that is shaft torque, watts. Okay. Where T is equal to motor output. EB into Ia is nothing but what? Motor output, mechanical power developed in the armature winding. That is motor output divided by 2 pi n by 60. 2 pi n by 60, that is Newton meters. Okay. So then if you are simplifying here, 9.55 into output by n I am getting, that is Newton meters. Okay. So now last torque is equal to last 2 pi n by 60. This is the 2 pi n by 60. Nothing but what? Here 9.55 into 9.55. This is the TSH. Okay. So this is the motor output. Motor output is equal to, I am getting here, I am writing here TSH is equal to, TSH is equal to motor output divided by 2 pi n by 60. 2 pi n by 60. Okay. So this is I am getting here torque. Okay. So then motor output I am writing here 9.55 into output by n. So from this equation I am writing T last torque is equal to armature torque and shaft torque. I am writing here. Last torque and T loss is equal to armature torque minus shaft torque. Means total last torque is equal to armature torque minus shaft torque I am getting in case of the DC motor. So this is the relationship between the three torques. What is that is? First, torque will be developed in the armature winding, that is called as a what? Armature torque. Torque will be developed at the shaft, the torque I am calling as a shaft torque. And torque will be developed due to of the loss, that is called as a what? Loss torque. Then the relationship between these three torques is equal to loss torque is equal to armature torque minus shaft torque. So this is about different types of the torques of the DC motor. And we discussed today back EMF of DC motor and the different types of the DC motors and the torque equation of the DC motor. Which torque that is? Gross torque or armature torque equation of the DC motor. And also we discussed the relationship between the gross torque and our armature torque or shaft torque and as well as the loss torque. That loss torque is equal to armature torque minus shaft torque. Okay. So this is about today's topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.